It's 2:13 a.m. The lab is mostly dark, except for the stubborn blue of a server rack and the soft glow of an oscilloscope that refuses to sleep. A fan ticks like an anxious metronome. On the screen, a clean stream of data, until one digit appears that shouldn't exist. No human touched the keyboard. No malware. No power spike. Just a single wrong bit. So here's the question that should make your skin tighten just a little. If the universe can reach into our devices, and into our genes, with single particles, how much of our stable world is actually built on chance? I'm Rowan K. Mercer. This is the Science Audit. And tonight we're doing something unusually intimate with the cosmos. We're tracing an invisible input stream that pours through your ceiling, your skin, your motherboard, and your atmosphere, unseen, unrequested, but measurable. Cosmic rays. Not the sci-fi kind. The kind that can flip a bit in a memory cell, nick a strand of DNA, or ionize a patch of air high above the clouds. And I need to set the stakes clearly, right now. This is not fear-mongering. This is clarity. We're going to quantify what's real, what's plausible, what's speculative, and what's still an honest question mark. Because cosmic rays are one of those phenomena that feel like philosophy until you realize there are engineers quietly designing around them, and biologists quietly accounting for them, in the real world. Let's begin somewhere you don't usually imagine yourself standing. Not on a mountaintop, not in a particle accelerator, but at the bottom of a waterfall. Except this waterfall isn't made of water. It's made of particles. A constant thin rain from space, sometimes gentle, sometimes furious, that collides with the top of our atmosphere like a fist into a pond. And what reaches you down here, at sea level, isn't usually the original punch. It's the splash. The spray. The cascade. That's the first audit point. When most people say, cosmic rays, they picture a single bullet from the stars hitting the ground. But Earth lives at the bottom of an atmospheric ocean. Incoming high-energy particles slam into air molecules tens of kilometers above your head. The impact turns the sky into a factory that manufactures new particles, secondary particles, that continue downward in a branching shower. So where do these primary cosmic rays come from? Three major sources matter for our story, and each one carries a different kind of uncertainty. First, galactic cosmic rays. These are the everyday background of high-energy particles coming from beyond our solar system, mostly protons, plus heavier nuclei. Think of them as shrapnel from ancient astrophysical violence. A likely accelerator? Supernova remnants, those expanding shock waves left behind when a massive star dies. Shock waves are nature's brutal conveyor belts. A charged particle can bounce back and forth across the shock front, gaining energy like a ping-pong ball in a hurricane. Not every detail is settled, but this picture is strongly supported. Second, solar energetic particles. These are cosmic rays with a local address. When the sun erupts, solar flares, coronal mass ejections, it can fling charged particles outward. If you've ever watched footage of a solar flare and felt it was purely visual spectacle, remember, it's also a particle event. It's the sun briefly becoming a more dangerous neighbor. Third, ultra-high-energy cosmic rays. Rare. Extreme. Energies so high they make our best human-built accelerators look modest. Their sources are still debated. Active galactic nuclei? Colliding galaxies? Exotic objects? We catch them like mysterious postcards with no return address. Now, here's where the story turns from cosmic to intimate. Because no matter where a primary cosmic ray begins, supernova shock, solar storm, distant unknown, it must pass one gatekeeper to reach you, the atmosphere. And the atmosphere doesn't just block it. The atmosphere transforms it. Picture it with me, right now, in real time. A single high-energy proton, maybe born near a supernova remnant thousands of years ago, arrives at the top of Earth's atmosphere at nearly the speed of light. It hits a nitrogen nucleus. And at that instant, the sky fractures into a branching tree. Not metaphorically. Physically. A cascade. The primary collision creates a spray of new particles, pions, kaons, all sorts of unstable intermediates that live for tiny fractions of a second. Then those decay into more familiar secondaries, electrons and positrons, photons, neutrons, and one that deserves special attention, the muon. A muon is like the universe's stubborn messenger. It's similar to an electron but heavier, about 200 times heavier, so it doesn't get deflected and slowed down as easily. It's born high in the atmosphere and then it barrels downward, passing through air, through buildings, sometimes through you, often through solid rock, before it decays. If cosmic rays are the storm, muons are the hailstones that actually make it to your front porch. They're one of the main reasons this subject isn't just space science. It's ground science. Human science. So how do we know any of this is real? Because we've built instruments that let the invisible leave fingerprints. A cloud chamber is one of the most poetic devices ever created in physics. You supersaturate vapor, and when a charged particle passes through, it ionizes the air, creates tiny charged seeds, and droplets condense along its path. You don't see the particle. You see its wake, like seeing a boat by the ripples it makes. Scintillators do something different. A particle hits the material and a tiny flash of light pops out, like a microscopic firefly signal. Photomultiplier tubes turn those flashes into electronic pulses. Balloon experiments ride up to the stratosphere to sample the shower closer to where it's born. Neutron monitors sit on the ground and count changes in secondary neutrons. And then there are the giant observatories, like the Pierre-Auger Observatory, that spread detectors across huge areas, waiting for the rarest, most violent showers to paint a pattern across kilometers. Now I want to slow down and translate two phrases that people throw around like they're self-explanatory. They're not. And if you misunderstand them, you'll misunderstand the whole ethical tone of this topic. Ionizing radiation. Here's the metaphor first. Imagine matter as a library where the books are atoms and the letters are electrons. Ionizing radiation is any visitor with enough energy to walk in, grab letters out of pages, and leave the text scrambled. In physics terms, it can knock electrons loose from atoms or molecules, creating ions and free electrons. That's a chemical disruption. Sometimes it's repaired, sometimes it isn't. Dose and flux. Flux is how many particles are coming through a given area, per time. It's the rain rate. Dose is how much energy is being deposited in tissue or material. It's the total soaking. High flux with low energy might be less damaging than low flux with extremely high energy. These numbers matter because they let us talk like auditors instead of mystics. Okay. We have the waterfall. We have the cascade. We have the measurement. Now we reach the edge of understanding, where cosmic rays stop being a distant astrophysics trivia fact and start becoming a question about your life. Because cosmic rays don't just exist. They interact. Let's start with the most intimate ledger in the universe, DNA. You're a city of cells, and every cell contains a library, your genome, copied again and again as you grow, heal, and age. And copying is never perfect. But most people imagine mutations as purely internal, errors in replication, chemical wear and tear, maybe sunlight. Cosmic rays add another category, edits from the sky. What does that actually mean in mechanism, not drama? Two main pathways. First, direct damage. A charged particle passes through a cell nucleus and deposits energy along the track. That energy can break chemical bonds. It can cause a single-strand break, like slicing one rail of a ladder. Or a double-strand break, both rails, more serious, harder to repair. Second, indirect damage. Even if the particle doesn't hit the DNA directly, it can ionize nearby water molecules. And water is most of you. Ionized water forms reactive chemical species, think of them as short-lived chemical vandals, that can go on to damage DNA and other molecules. Now here's the part that protects us from turning this into cosmic paranoia. Biology is not helpless. Cells have repair systems. They patrol DNA. They fix many breaks. They correct many mistakes. If they didn't, complex life wouldn't last a week. So what's the audited statement? Cosmic rays contribute to the background rate of DNA damage and mutation, but mutations are still rare relative to the total number of particle tracks. Rare, though, is not the same as zero. And over long timescales, evolutionary time, lifetime time, non-zero becomes meaningful. If you want to feel this in your body, imagine each muon as a silent needle passing through a vast quilt. Most passes don't snag a thread. But sometimes, somewhere in the quilt, a stitch shifts. And if that shift occurs in the wrong place, in the wrong cell, at the wrong time, biology notices. Now let's walk from wet biology to dry silicon, without losing the wonder. Because the exact same kind of physical event, ionization along a microscopic track, can also become an error in a computer. This is where the server rack at 2:13 a.m. stops being a cinematic prop and becomes a real case file. Computers store information as charges, as voltages, as tiny regions of more electrons, or fewer electrons. A bit is a yes or no decision built out of physics. And modern transistors are so small, so delicate, that a single charged particle can carry enough punch to upset that decision. The term of art is single event upset. Here's the metaphor. Imagine a marble balanced in a shallow bowl. The bowl's shape represents the stability of a stored bit, 0 or 1. Most vibrations don't move it out. But a sharp tap at the right angle can knock it over the rim into the neighboring bowl. One particle. One tap. One flipped bit. Mechanistically, what happens is simple and brutal. A charged particle deposits charge in a sensitive region of a transistor or memory cell, called a node. If the deposited charge is large enough, the circuit interprets the state incorrectly. A stored 0 becomes a 1, or a 1 becomes a 0. Why does this matter more now than decades ago? Because we've been shrinking everything. Smaller transistors. Lower voltages. Denser memory. And when the margin between 0 and 1 gets thinner, the universe doesn't need to hit as hard to cause confusion. You might be wondering, does this only matter in space? Only on satellites? Only on airplanes? No. It matters there a lot, because higher altitude means less atmosphere above you, which means less shielding, which means more of the shower survives. Aviation and space electronics are more exposed. That's audited and uncontroversial. But even at ground level, servers can see occasional errors attributable to cosmic rays. It's not constant chaos. It's a low-level statistical reality. But if you run enough memory for long enough, data centers do, you'll eventually meet the sky in your error logs. And engineers, quietly, pragmatically, already fight back. ECC memory, error-correcting code, is like sending each message with a little built-in redundancy so that if one letter flips, the system can detect it and often correct it. You can harden designs. You can add redundancy. In spacecraft, you can choose radiation-hardened components. In aviation, you can plan routes and altitudes with space weather in mind. This isn't superstition. It's resilience engineering. Now I want to take you to the most controversial ledger in our audit, and we're going to be unusually careful here. Because this is where people tend to overclaim. Clouds? Here's the seduction. Cosmic rays ionize the atmosphere. Clouds depend on aerosols, tiny particles, because water vapor needs something to condense on. So maybe cosmic rays influence cloud formation by helping create those condensation seeds. And if clouds change, climate changes. Simple chain. Clean narrative. A cosmic lever on Earth's thermostat. But nature is rarely that obliging. Let's separate what's solid from what's uncertain. Solid, ionization changes atmospheric chemistry. It creates ions. It influences how molecules stick together. Solid, cloud formation depends on aerosols, cloud condensation nuclei, and the availability of water vapor and the temperature and atmospheric dynamics. Uncertain, the size of the cosmic ray effect in the real, messy atmosphere compared to dominant drivers like temperature profiles, humidity, existing aerosol pollution, sea salt, dust, organic compounds from forests, volcanic emissions, and large-scale circulation patterns. The atmosphere isn't a clean laboratory flask. It's a turbulent, layered, chemically diverse reactor. So when you hear, cosmic rays control the weather, The audit response is, show me the causal chain, show me the magnitude, show me the accounting against the bigger terms. Because correlation is cheap. Causality is expensive. And here's why causality is especially tricky in this case. The sun modulates cosmic ray flux. When solar activity is strong, the solar magnetic field and solar wind tend to provide more shielding against incoming galactic cosmic rays. Fewer reach Earth. When solar activity is weaker, more galactic cosmic rays can penetrate. So you can observe cycles. You can observe changes. But if cloud properties shift with solar cycles, what's doing the shifting? Is it cosmic rays? Is it changes in ultraviolet radiation affecting ozone and stratospheric temperatures? Is it subtle shifts in atmospheric circulation? Is it multiple variables braided together? This is where the scientific process becomes a form of humility. Now, breathe for a second. Because we've gathered 3 threads: DNA, computers, clouds, and they might feel like separate topics. But they're about to lock together. And when they do, you're going to feel the ground under reality shift just slightly. Imagine one single ionizing track. 1. A muon passes through matter. Along its path it strips electrons from molecules, leaving a trail of ions and excited states. That physical track is the same track in all cases. But what it becomes depends on the system it passes through. In DNA, the track is damage, a break, a base modification, a biological problem to repair. In a microchip, the track is error, a flipped bit, a computational misstep, a logic hiccup. In the atmosphere, the track is chemistry, an ion pair, a potential seed, a subtle nudge in a chain of reactions. Same event. 3 interpretations. 3 worlds. That's the eureka. The universe doesn't change its behavior to match our categories. We label it after the fact based on what we care about: health, computation, climate. But underneath those labels is one indifferent physical process: energy deposition in matter. And once you see that, you start noticing it everywhere. The boundary between random noise and meaningful effect isn't a wall. It's a negotiation. A negotiation between statistics and stakes. So let's land the philosophy carefully, like setting down a delicate instrument. At human scales, we crave determinism. We want the world to be a clockwork, clean inputs, clean outputs. But the audited reality is stranger. The world is statistically stable. Not perfectly deterministic. Stable because countless microscopic events average out, like the surface of the ocean looking smooth from an airplane even though it's made of uncountable waves. Cosmic rays are a perfect demonstration. Most of the time, they pass through you and nothing happens that you notice. Most of the time, they pass through a computer and the system corrects the error, or the error lands in an unused bit and vanishes. Most of the time, they ionize air and it never becomes a cloud droplet. But sometimes they do matter. And the moment you build a device delicate enough, or a biological system complex enough, or a planet-scale atmosphere sensitive enough, sometimes becomes worth auditing. Now, I want to be explicit about what randomness means here, because people hear random, and they think mystical. Or worse, they think anything can happen. Randomness in this context is measurable noise with patterns. Flux varies with altitude. With latitude, because Earth's magnetic field guides charged particles. With solar activity, because the heliosphere breathes in and out like a magnetic lung. And because it has patterns, we can mitigate. We can engineer. That's one of the most human things we do. We don't demand a universe without chaos. We build systems that remain trustworthy in a universe with chaos. ECC memory. Redundant flight systems. Radiation-hardened circuits. Space weather forecasting. Even simple shielding choices in design. And then there's the awe. The kind you feel when you realize your body is, in a quiet way, a detector. Right now, as you watch this, particles are passing through you. Through your skull. Through your chest. Through the soft saltwater intelligence of your brain. Most are harmless. All are messengers from violent engines, exploding stars, magnetic storms on the sun, distant galaxies that fling particles across interstellar space. You are not sealed off from the cosmos. You are immersed in it. And that brings us back to climate, because it's the place where people most want a single lever, a single culprit, a single savior variable. The audited stance is more sober and, honestly, more beautiful. The atmosphere is a sensitive chemical reactor, and cosmic ionization is one input among many. Not the puppet master. Not irrelevant. A contributor whose magnitude is still being pinned down. So what have we learned, really, on this journey from a wrong digit on a server to the top of the sky? We've learned that Earth sits beneath a particle waterfall. That primary cosmic rays strike the atmosphere and create showers, with muons as the ghostly ground-level messengers. We've learned that ionizing tracks can break bonds in DNA, flip bits in computers, and alter chemistry in air. We've learned that our world's stability is statistical, and that the line between noise and event depends on context, vulnerability, and time. Now I want to leave you with a thought experiment, something you can carry into tomorrow morning when you're making coffee, when your phone unlocks, when you look at a cloud and think it's just a cloud. Imagine a single cosmic ray particle that begins its journey near a dying star. It travels for centuries or millennia through magnetic fields and emptiness. It reaches Earth tonight. It hits the atmosphere. It becomes a shower. And one of its descendants, a muon, passes through your home. It passes through your device. It passes through you. Ask yourself, if that single, ancient traveler can make a microscopic edit, one flipped bit, one chemical nick, one ion pair, then what else in your life that feels solid is actually being stabilized moment by repair, correction, redundancy, and resilience? And then the next great question opens quietly, like a door you didn't know was there. If the universe can write tiny edits into matter, what else in our stable reality is actually a living negotiation with the cosmos? If you want to keep going, I have a video waiting for you on the end screen that takes this same auditing lens and pushes it into an even stranger corner of reality. Click it and stay in the investigation. And before you go, have you ever experienced a mysterious computer crash, corrupted file, or unexplainable glitch that made you suspect something deeper? Yes or no, and where were you when it happened? Subscribe if you want more audits like this. Not hype, not hand-waving, just the most honest map we can draw of what's real, what's uncertain, and what it means to be human in a universe that still reaches us, one particle at a time.